Before we begin, please set up the next page in your journal. It is page 7. Your title is Interpreting Motion Graphs. What we're going to do today is look through how to get velocity off of a position time graph, and then how to take that velocity and put it on a velocity time graph. Pause the video now if you need the extra time to set up your journal. Before we begin looking at graphs, there are some basic rules that you need to know about reading a graph. Please write this information on page 7. Leave some space at the top to glue your handout. When you're looking at a position time graph, a positive slope, meaning going up and to the right, means that the object is moving forward in a positive direction and has positive velocity. A negative slope, meaning down and to the right, means the object is moving backward or back toward the origin. It also has a negative velocity. If you have a zero slope on a position time graph, that means the object is not changing position, so it is not moving, and we know that that means it has a zero velocity. When you're looking at a velocity time graph, those graphs look a little unusual. And so it's important to have some guidelines by your side when you're trying to read a velocity time graph. If the line is positive, a positive velocity means the object is moving forward or away from its origin. If the line is negative, a negative velocity means the object is moving backward or back toward its origin. A zero velocity means that the object is not moving. But in this case, a zero slope or a flat horizontal line just means that the object has a constant velocity. Pause the video now if you need the extra time to copy this onto page 7. Now we'll look at some examples. One of the example graphs that you have on your handout looks like this: a position time graph with a positive slope line and then a flat part and then another positive slope to the line. Our ultimate goal is to translate this graph onto our velocity graph, which is at the bottom of your handout. Now, the first thing that we need to do is to calculate the velocity at each section of our line on the position graph. So one of the first things that we need to do is figure out what is the actual position of our object here. And you can see in the first section, 0 to 4 seconds, we need to see where the object has moved to and from. We know that it's going to end at the position of 2.1 meters at the 4-second mark. And we know that it began at the position of 0.9 meters at the 0-second mark. Now we also know that our equation for velocity is v equals d over t. So we need our distance and we need our time. In order to find the displacement of our object, we take where it ended here at 2.1 and subtract where it started over here at 0.9. Always do end minus start. Then for the time, we can do the same thing. We're looking specifically at our time code 0 to 4 seconds. So we do our where did we end at for time, minus where did we start at for time. When we continue on with that math, 2.1 minus 0.9 gives us 1.2 meters divided by 4 seconds. If you put that in your calculator, you end up with 0.3 meters per second. So that's our velocity for this first part of the line between 0 and 4 seconds. We're going to look at where did the object finally end. Excuse my writing down at the bottom here. Just adding in what we already knew before. 0.3 meters per second for the first chunk, 0 meters per second for the second chunk. For the last part, we're going to look at where did the object finally end up, which is at 3.3 meters at 10 seconds. Where did it start is 2.1 meters at 6 seconds. So we're going to go back to our equation. Velocity equals displacement over time. We're going to find our displacement. So 3.3 meters minus 2.1 meters. Then we're going to find our time. 10 seconds minus 6 seconds, because that's where we started at. And when you do that, it gives you 1.2 meters divided by 4 seconds. When you put that in your calculator, you get, just like for the first part, 0.3 meters per second. So now we found our velocity for each leg of our trip here. 0.3 meters per second here, 0 in the middle, and 0.3 meters per second again over here. Now we need to know how to graph that. So the first thing that you'll do is take your known velocity, and excuse me while I make some corrections over here. You know that your velocity between 0 and 4 seconds is going to be a constant 0.3 meters per second. So what we've done is make a dot. At 0 seconds, we start at 0.3 meters per second, right here. At 4 seconds, we're still going 0.3 meters per second, so we made another dot there. And then the next thing that you have to do is draw a line to connect them. So you can see that we've got our first part of our graph here. Now the next section, we know that we're moving at 0 meters per second between 4 and 6 seconds. So we do the same thing. At 4 seconds, we put a dot at 0. At 6 seconds, put a dot at 0. and then we just draw a line to connect them right here. For the last chunk, 6 to 10 seconds, we do the exact same thing. At 6 seconds, and again at 10 seconds, put a dot at the velocity we know that we're going. And then you draw a line straight across because we know it's a constant velocity. It's not changing its speed at any point during that part of the trip. Now you can leave it just like this as 3 disconnected pieces of a line, and that is completely appropriate. Or you can connect your sections of line either with solid lines or dotted lines. Either one is acceptable and either one is appropriate. Now let's look at the next graph. This one's a little bit more difficult just because it has some negative direction. Now we're going to calculate everything exactly the same way. We look at our end minus our start to get the displacement for each leg of the trip. End minus start. We always do end minus start. If you look at the first piece of the line, we end at 1.5 meters and start at 3 meters. So we do 1.5 meters minus 3.0 meters to give us the top part of our equation. Now 1.5 minus 3 gives us a negative 1.5 meters. When you divide that by your time, which is 1, 2, 3 seconds, if you put that in your calculator, you're going to get a negative 0.5 meters per second. Now the next piece of line is a little bit simpler, because if you look at the next section of line, we're not moving at all. And remember, when you have no change in position, you have no displacement, which means that your velocity automatically is 0 meters per second. We don't even have to do any calculations there. We just already know. Now the next piece of line is going down again. We've got a negative slope, so we know that we're going to have a negative velocity. Let me just fill in our already knowns here. Now for this piece of line, we can see that we're ending after this 1 second at 0.6 meters, and we started at 1.5. So we go 0.6 meters minus 1.5 meters. In this case, we're only taking 1 second, so divided by 1 second. 0.6 minus 1.5 gives us negative 0.9 meters divided by 1 second gives us a velocity of negative 0.9 meters per second. Now, the next piece of line is easy as well, because you can see that the next piece of line is also not moving. So we can look at this line starting at 0.6 meters, ending at 0.6 meters, and know automatically that our velocity is 0 meters per second. So we've got negative 0.5, we have 0, and we have negative 0.9 meters per second, and then another 0. So the object was moving in the negative direction for 3 seconds, then it stopped for a second, then moved back in the negative direction for 1 more second, then stopped for 2 seconds. And now we'll see what happens next. We've got one more piece of line here. And this time, the slope is positive because the line is going up and to the right. So this process is exactly the same. We take where did we end, subtract where did we start, that gives us our displacement, and then divide that by the time. Now in this case, our displacement would be 3 minus 0.6, which gives us 2.4 meters, divided by our time, which is 1, 2, 3 seconds. When you plug that into the calculator, you get 0.8 meters per second, positive 0.8 meters per second. So now what we have to do is put all of this onto our graph. So the first thing that we do is we take our first velocity, which is negative 0.5, and we draw a line from 1 to 3 seconds at the negative 0.5, because the object was going at that constant velocity for that entire time period. Then between 3 and 4 seconds, the object jumped up and was moving at 0 meters per second. It stopped. After that, it was going a negative 0.9, so we add our piece of a line there. Excuse me. And then it stopped again for 2 seconds, so we add our piece of a line there at 0. And then finally the object was moving at a positive 0.8 meters per second. And again, you can leave your lines separated like this, or you can connect them if that makes you feel a little bit more comfortable. Some people have a really hard time looking at just the disconnected lines. I sincerely apologize for my errors down here in the velocity section. So just to double check that you've got all of your information, negative 0.5 meters per second for the first piece, 0 meters per second for the second one, negative 0.9 meters per second, then 0 again, and then 0.8 meters per second. I also will have the full correct PowerPoint on Canvas if you would like to click through the PowerPoint, and it will have all of the individual steps that I didn't have space to write out on this video, and hopefully that will make sense. If you have any questions, please make sure to contact me or come in for tutorials.